After the Big Bang, the dance of the universe's cyclical circulation began. Light and matter, like sparks in empty space, emerged and created the world. Time flows, drawing the splendid shadows of the universe, and stars continue to tell stories, passing them on through generations. The Big Bang, originating from the depths of the galaxy, has taken its place alongside the endless flow of time in the vastness of the universe. Our eyes catch a glimpse of the history of the universe, the dance of stars, the tranquility of galaxies, the birth and disappearance of planets. The universe beckons us with an unknown dialogue, and we are constantly captivated by its mysteries. Time envelops us as a gift, conveying traces of the past and descriptions of the future. Our understanding challenges the mysteries of the universe, but in the face of the infinite cosmos, our understanding is small and limited. Like stars departing as light, our ultimate destiny will one day return to the universe. The evolution of the universe, through the infinite tunnel of time, is advancing beyond our limits towards profound mysteries. Today, in the 6th session of Introduction to Astrophysics, let's explore how scientists explain the topics of energy, matter, gravity, and time. Subscriptions and likes greatly empower video production. The state of the universe before the Big Bang has not been definitively determined. However, based on current research results and hypotheses, it is estimated that the pre-Big Bang universe was in an extremely high energy and dense state. In this state, matter and energy would have exhibited quantum characteristics, and the phenomenon of mutual transformation would have occurred repeatedly. Therefore, it is challenging to simply state that there was only energy and no matter before the Big Bang. The pre-Big Bang universe remains a realm of unknowns in physics, requiring further research and experimentation. Dr. Hawking attempted to explain the pre-Big Bang using the no-boundary proposal theory. This theory suggests that the boundary conditions of the universe have no boundaries, and time and space originated from the Big Bang. Since time did not exist before the Big Bang, events before it cannot be defined, according to this proposal. After the Big Bang, there was a process of energy transforming into matter. In the early universe, after the Big Bang, conditions were characterized by extremely high temperature and density. During this time, energy and matter interacted and transformed. According to Einstein's famous equation, E=mc2, in other words, energy converted into particles with mass, and vice versa, in a repeating cycle. Through this process, primordial particles were created, and they collided or combined to generate various forms of matter. For example, quarks and gluons combined to form nuclear particles, like protons and neutrons, and nuclear particles combined with electrons to form atoms like hydrogen and helium. These atoms, influenced by gravity, came together to form stars and galaxies. This explanation covers the process of energy transforming into matter after the Big Bang. The Big Bang enables a deeper understanding of the origin and structure of the universe, as well as the relationship between matter and energy. This passage discusses the gravitational effects in fermionic and bosonic states, or energy states. Fermions are particles with half-integer spin that follow the Pauli exclusion principle. Examples of fermions include quarks, leptons, and baryons. Energy states, in the context of quantum mechanics, represent the possible values of energy a physical system can have. These states are expressed in terms of quantum numbers, and lower energy states are filled sequentially. In fermionic or energy states, it is difficult to say that gravity exists inherently. Gravity, as described by general relativity, acts as a force on all matter and energy in the universe, curving space-time. Therefore, if fermions or energy states have mass or energy, they can generate and experience gravity. For instance, neutron stars or white dwarfs are celestial bodies supported by the pressure of fermions like neutrons or electrons. Despite their small size compared to their mass, they exhibit strong gravitational effects. However, the gravitational force in fermionic or energy states is considerably weak compared to other forces. Fermions are influenced by other fundamental forces, such as strong force, weak force, and electromagnetic force, which are much stronger and determine the behavior and interactions of fermions. For example, quarks, influenced by the strong force, form composite particles called hadrons, and electrons. Energy states are determined by quantum mechanics, and the compatibility of gravity with quantum mechanics has not been fully elucidated. Quantum gravity theories attempt to describe gravity in a quantum mechanical framework. Bosons, on the other hand, have integer spin and do not follow the Pauli exclusion principle. Examples of bosons include photons, gluons, and gravitons. Bosonic states represent the possible states of a system composed of bosons. These states are distributed according to Bose-Einstein statistics, and bosons can share the same quantum state. Similar to fermions, bosonic or energy states do not inherently possess gravity. Gravity, described by general relativity, acts as a force on all matter and energy in the universe, curving space-time. Therefore, if bosons have mass or energy, they can generate and experience gravity. For example, photons, having energy and momentum, are influenced by gravity. Gravitons, hypothesized as the carriers of gravity, would also be influenced by gravity if they have mass. Gravitons, hypothesized as the carriers of gravity, would also be influenced by gravity if they have mass. However, the gravitational force in bosonic states is weak compared to other forces. Bosons are influenced by other fundamental forces, such as strong force, weak force, and electromagnetic force, which are much stronger and determine the behavior and interactions of bosons. For example, photons are reflected, refracted, absorbed, or emitted due to electromagnetic force. The gravitational force of bosons, like gravitons, needs to be described through quantum gravity theories, although there is currently no definitive evidence or theory. Gravitons are hypothetical virtual particles that mediate the gravitational force. Predicted by quantum gravity theories, gravitons have spin 2, no mass, and transmit only gravity. They interact with all matter and energy in the universe, creating the curvature of space-time. Gravitons, however, have not been observed, and quantum gravity theories lack definitive evidence or consensus. Quantum gravity theory is a field of theoretical physics aimed at describing gravity in a quantum mechanical framework. There are several contenders within the realm of quantum gravity theory, each proposed by different scientists. For instance, string theory, developed in the 1960s by researchers such as Gabriele Veneziano, Yoichiro Nambu, Leonard Susskind, and Holger Beck-Nielsen, represents all fundamental forces, including gravity and particles, as one-dimensional strings. Loop quantum gravity, formulated in the 1980s by Abhay Ashtekar, Carlo Rovelli, Lee Smolin, Ted Jacobson, etc., quantizes the gravitational field and represents space-time as loops and networks. Causal dynamical triangulation, developed in the 1990s by Renate Loll, Jan Ambjörn, Jerzy Jurkiewicz, involves dividing space-time into triangles, considering quantum fluctuations, and exploring the quantum aspects of the geometry. Entropic gravity, proposed in the 2000s by Eric Verlinde, describes gravity in terms of changes in entropy. Twistor theory, introduced in the 1960s by Roger Penrose, seeks to unify gravity and quantum mechanics using complex numbers and the concept of twistors. Dr. Hawking did not advocate for a theory of quantum gravity. Quantum gravity theory is a field in theoretical physics that aims to describe gravity in terms of quantum mechanics. Dr. Hawking conducted research related to black holes as part of the framework of quantum gravity theory. He famously demonstrated that black holes emit thermal radiation, termed Hawking radiation. Additionally, he proposed several hypotheses regarding the information loss problem associated with black holes. However, Dr. Hawking did not complete or verify a theory of quantum gravity. He described his research as a step toward quantum gravity theory, but not its completion. Dr. Hawking supported and advocated for efforts to find a theory of quantum gravity. The Higgs particle is one of the fundamental particles suggested by the standard model of particle physics, playing a role in giving mass to other particles. It was discovered in 2012 at the Large Hadron Collider, LHC, at CERN, and its currently known mass is approximately 125.9 GeV-2. The Higgs particle has no spin or charge and interacts only through weak and Yukawa interactions, making it a scalar boson. The discovery of the Higgs particle is of great significance in modern physics for understanding the constituents of the universe and their interactions. The discovery of the Higgs particle is of great significance in modern physics for understanding the constituents of the universe and their interactions. It completes the standard model of particle physics by providing mass to other particles, which is essential for explaining the universe. The Higgs field, through the Higgs mechanism, imparts mass to other particles and permeates throughout the universe, represented by the Higgs boson. The discovery of the Higgs boson in 2012 at the Large Hadron Collider marked a historic milestone in modern physics. Regarding black hole entropy theory, physicist Jacob Bekenstein proposed in 1972 that black holes should possess well-defined entropy. This idea was later complemented by Stephen Hawking's discovery that black holes emit thermal radiation, contributing to the foundation of black hole thermodynamics. Various perspectives exist on how this theory might effectively explain the origin and evolution of the universe. One viewpoint associates the entropy of black holes with the overall entropy of the universe. Universe entropy increases with its expansion after the Big Bang, making it a crucial concept in explaining the universe's form and evolution. The entropy of a black hole is a physical quantity observable from outside, regardless of the internal state of the black hole, playing a crucial role in addressing the black hole information loss problem and understanding quantum gravity. Additionally, studying the entropy of black holes and the principles of quantum mechanics aids in comprehending the peculiar phenomena of the universe. For instance, research into the unique structures of the universe, such as black holes, has profoundly influenced the establishment of quantum gravity and the holographic principle. This is a brief explanation of the scientist who proposed the theory of black hole entropy and how this theory can provide insight into the origin and evolution of the universe. History of Time by Dr. Stephen Hawking is a popular science book that introduces the latest knowledge of the universe and time in an accessible way. In this book, time is explained as one of the fundamental characteristics of the universe, essential for understanding all phenomena in the cosmos. Dr. Hawking argues that time is not absolute, but a relative concept that can vary depending on the observer. According to the general theory of relativity, gravity is a force that bends space-time. Therefore, The closer an observer is to a gravitational field, the slower time appears to pass for them. For example, an observer near a black hole would experience time passing more slowly than an observer farthest away from it. Dr. Hawking claims that time plays a crucial role in the origin and evolution of the universe. According to the Big Bang theory, the universe started approximately 13.8 billion years ago from a singularity, a state where time and space were infinitely distorted and the laws of physics did not apply. Hence, a physical description of the universe before the Big Bang is deemed impossible. Dr. Hawking also asserts that time is significant in the end of the universe. If the universe continues to expand, it will eventually reach a state known as heat death, where all matter is scattered and the temperature becomes uniformly distributed, rendering time meaningless. In History of Time, Dr. Hawking provides various perspectives on time, contributing to our broader understanding. The specific content regarding time in the book can be summarized as follows. Time is not absolute, but relative. Time plays a crucial role in the origin and evolution of the universe. Time is significant in the end of the universe. Dr. Hawking defines time in History of Time as follows. Time is the measure of the rate of change, and the passage of time measures the extent of change that has occurred. According to this definition, time is a tool for measuring changes in physical phenomena. Therefore, time is not absolute. It can vary depending on the observer's perspective. Dr. Hawking divides the history of time into 3 parts in the book. The beginning of our universe, explanation of the origin and evolution of the universe, focusing on the Big Bang, expansion, inflation, and dark energy, the nature of time and space, explanation of the nature of time and space based on general relativity and quantum mechanics, the end of time, explanation of the possible outcomes for the end of the universe based on its expansion. Dr. Hawking explains the origin of the universe as follows. The universe began with the Big Bang approximately 13.8 billion years ago. Before the Big Bang, the universe was infinitely small and hot. After the Big Bang, the universe rapidly expanded to become the universe we know today. Regarding the state of the universe before the Big Bang, Dr. Hawking speculates that before the Big Bang, we still don't have a precise understanding of the universe. However, it is conjectured that before the Big Bang, the universe was in a state known as a singularity. A singularity signifies a state where time and space were infinitely distorted. Flow of time. According to Dr. Hawking, in the framework of general relativity, the flow of time is described as follows. Time's flow is altered by gravity. In regions with strong gravity, time passes slowly, while in regions with weak gravity, time passes quickly. Dr. Hawking illustrates this flow of time with the following example. The distance light travels in 1 second on the surface of Earth is about 300,000 kilometers. However, due to the gravity of a black hole, light only travels about 100 meters in 1 second. Therefore, within the gravitational pull of a black hole, time flows around 3 million times slower than on the surface of the Earth. End of time. Dr. Hawking explains the end of the universe as follows. The end of the universe depends on the rate of its expansion. If the universe's expansion rate decreases, it will eventually contract back into a big crunch. Conversely, if the universe's expansion rate increases, it will expand forever without end. Dr. Hawking proposes 2 possibilities for the end of the universe. Big Rip. The universe expands indefinitely, and eventually, all matter and energy are torn apart, leading to the end of the universe. Big Freeze. The universe contracts, and eventually, all matter and energy freeze. leading to the end of the universe. In A Brief History of Time, Dr. Stephen Hawking describes time as one of the fundamental elements constituting the universe. Time is the measure of change in the physical realm, and all physical processes in the universe change according to the flow of time. Dr. Hawking emphasizes that time is not absolute. It can be perceived differently by observers. For instance, the time of a space traveler moving at the speed of light would pass slower compared to someone on Earth. Dr. Hawking discusses two major theories of time's essence in physics: general relativity and quantum mechanics. According to general relativity, time is a dimension of space, and it changes with the expansion and contraction of the universe. Quantum mechanics suggests that time is discrete, and time reversal is possible in the quantum realm. Dr. Hawking also discusses the end of time. Due to the impossibility of providing a physical description of the universe before the Big Bang, predicting the end of the universe is also challenging. Dr. Hawking argues that the end of the universe could be one of the following: Big Crunch, Big Freeze, or Big Rip. In A Brief History of Time, Dr. Hawking presents various perspectives on time, contributing to broadening our understanding of its essence. He divides the discussion into 4 parts. The history of our universe. This part covers the origins and evolution of the universe, focusing on topics such as the Big Bang Theory, the expansion and contraction of the universe, inflation and dark energy, the nature of time and space. Here, Dr. Hawking explains the essence of time and space, discussing their relationship based on general relativity and quantum mechanics, the singularities of black holes. This section explores the singularities of black holes, discussing their formation, characteristics, and the significance of singularities. The future of the universe. Dr. Hawking addresses the possible fates of the universe, including the Big Crunch, Big Freeze, and Big Rip. Through these discussions, Dr. Hawking expands our understanding of time and presents new perspectives on the origins and evolution of the universe. Time is a crucial tool in understanding the universe, yet it remains a mysterious entity that we have not fully grasped. The History of Time is a book aimed at the general public, but it contains vast knowledge and insights into cosmology. This book is widely regarded as a significant contribution to expanding our understanding of the universe. After the prelude of the Big Bang, the cosmic dance began, illuminating the darkness and giving birth to the world. The evolution of the universe is an infinite symphony, with stars dancing at every branch of the galaxy. Vividly described to us, the ceaselessly flowing time leaves behind mysterious traces of the universe, conveying life's story to us. In the depths of the galaxies, the cosmic festival continues, with planets and stars weaving tales in every moment. Though stars silently depart, we etch their departed traces onto the pages of time. The universe unfolds a book of hope for us, revealing the intertwined flow of past and future through the passage of time. Our understanding continually faces challenges, and in the infinite embrace of the universe, we become small lights, shining. Exploring the endless cosmos takes us beyond our limits into the mystery of time and the universe flowing together.